Hello, students. Welcome back. This will be my Unit 2 webcast on enzymes. And so here we go. We're going to dive right in. I really thought you did a great job with the catalase lab in class, the liver and the hydrogen peroxide. Hopefully that helped you to see enzymes in real life. And so you were able to determine for yourself how temperature and pH affected them, whether or not they were reusable, etc. I always think we learn better from doing, and I really hope you found that to be the case. All right, so thank you, Ms. Vogel, for these slides that we're going to go through. I added a couple of my own. And let's see. Ask yourself these questions. Can you answer these? This enzyme should be a little easier than the last podcast. What's a quick and easy way to tell if something is an enzyme or a carbohydrate? Hint, think about spelling. How does an enzyme work? Use those words substrate and active site in your answer. What is activation energies? What do enzymes do to activation energy? Enzymes are substrate specific. What does this mean? Hint, discuss the lock and key analogy. What is meant by denaturing an enzyme? What items can denature an enzyme? And in this one wasn't in your book, but I added it in. Compare and contrast competitive and non-competitive inhibitors. All right, let's get rolling. Okay, enzymes are proteins that speed up chemical reactions. They make them go faster by lowering the activation energy of reactions that would normally happen anyway. So here, H2O2, which is hydrogen peroxide, would break apart into water and oxygen on its own. That's why it's in a brown bottle. But in your body and in living organisms, like the yeast we use, they're going to have catalase in them that's going to make it go faster. And the way they make the reaction go faster is that they lower the activation energy. So by lowering the activation energy, you're going to get a quicker time to the products. So how does it work? Well, enzymes are used to build up molecules or to break them down. They're often called catalysts. Every cell is going to have hundreds of thousands of enzymes. They're proteins. They're going to be specific. They're named for the reaction they help. So sucrase is going to help break down sucrose. Proteases break down proteins. Lipases break down lipids. And DNA polymerase helps to build DNA. So enzymes don't always have to break things down. They can also help to build them up. Here's the lock and key analogy. I think it's on the next one. Oh, and look, they all end in ASC. Carbohydrates end in OSE. Sucrose, fructose, galactose, lactose. Whereas enzymes end in ASE, like sucrase or lactase. They're not used up, so hopefully you saw this in your lab when you poured the hydrogen peroxide on the liver that was already used once. It should have still bubbled because the enzymes were there and it was able to catalyze a reaction. So they can be reused. So this enzyme, this purple enzyme right here, is able to be reused. It's the shape that matters. Here comes the lock and key. Okay, in class, I picked the student's name and I said, hey, you can't get in their house unless you have their key. Right? Your key is specific to your house. Each enzyme is specific to its substrate. So sucrase only works on sucrose. That's why you have to have thousands of different enzymes. This is another good example of how the structure of a molecule leads to its function. The structure of this protein, or these R groups, and their interactions are going to create this shape that's going to be able to work with sucrose. Here's some vocab for you. So you should be able to look at these and label them. This would be the enzyme. This would be the active site. And this would be the substrate. Notice how it fits right in there. It's perfect, like a lock and key. If you did the advanced working class, you might have learned about the induced fit model, which would be good for you. And their products are what's going to come out. Okay, what affects enzyme activity? Think back to your lab. See if you can think about it. Well, it has to be the correct protein structure. It's got the correct order of amino acids. If there's a mutation, say you've been smoking, vaping, doing something bad for your DNA, then maybe the protein that would be made would be improper. It needs to be the right temperature. If it's at a different temperature than what it's supposed to be, the enzyme shape is going to change. And it's called denaturing. And it's got to be at the right pH. So the R groups are subject to pH changes, acids or bases, and it would change the shape of the enzyme. So here's an example. So here we changed the order of the amino acids. Well, it changed how they interacted. And look at how different the shapes of these proteins are. So the amino acid the enzyme would serve a different function, or it wouldn't work. Okay, temperature. Usually for us, it's going to be between 35 and 40 degrees Celsius. Our body temperature is 37 degrees Celsius. It could be different, right? We've looked at, there's an enzyme Taq polymerase, which deals with bacteria in hot springs, and that can be at a really hot temperature, et cetera. So what happens if we raise the temperature or boil it? What happened to your liver when you boiled the liver? What happened to the reaction? Well, it probably didn't work. I think almost everybody I've been looking at your labs online got 0 as the reaction right there. So you denatured the protein, it unfolded, it lost its shape, it's no longer able to work. At a lower temperature, molecules move more slowly. You've probably seen drops of food coloring put in ice water versus hot water. So it's going to move a lot slower. So there'll be fewer collisions between the enzyme and the substrate. So there'll be a slower activity rate. pH. So it depends on where it is in the body, right? So most of them will work between 6 and 8, but some of them, your stomach's more acidic. The enzymes in your stomach are going to work well at a pH of 3. Your small intestines are more basic, so trypsin, an enzyme in your small intestine, works better at a pH of 8. Here's a nice graph to show it. The red being neutral, the blue being trypsin, the green being pepsin. So you can see that they're going to work best at the pH there where they take place. So stomach versus intestines. All right, last but not least, inhibitors. Okay, this is not in your textbook. So we can inhibit or we can compete with enzymes so that they don't work as well. We compete directly with the substrate for the active site, or we can bind to another part of an enzyme and change its shape. So if this is my enzyme, I might bind here and change its shape so it doesn't work as well. This can be reversible, something temporary, which is what a lot of drugs do, a lot of prescription drugs do. Or it could be irreversible, permanent, like cyanide poisoning. Here are some examples. You don't need to memorize these, but penicillin is going to compete for the active site. It's going to block an enzyme that bacteria use to build cell walls. Antabuse is a medicine that's going to help to block the enzyme that breaks down alcohol, so it's going to make people who are trying to quit drinking feel bad. We're going to have anti-cancer drugs can inhibit enzymes involved in DNA synthesis. This would be non-competitive. So here's a good example. Non-competitive is binding onto this part of the enzyme and changing the active site so it doesn't work. Cyanide poisoning does the same thing. All right, there are some slides in Google Classroom that they take it a little bit to the next level, more to an AP level. You can check this out if you like, but I feel like this is a lot of information. This is enough for you to practice for your Unit 1 and 2 tests. I wish you the best of luck. You got until September 26th. You've got plenty of time to meet with me, and we're going to review a lot in class. Good luck, students.